Okay, so I think that's all about the biomass estimation, the kind of concept and what we did, what I have done in the past. Let's next is intro to R and its application. I think I talked with Joshua and he said most of the participants you have done used R, or you have seen R in previous seminars as well. So briefly, R is an open source programming language, and it's free, so that's good. And it's not only used by the statistician, but also forestry professionals like biometricians and other like ecologists, and everyone uses R these days if they are doing some data analysis. And why do we use R is because it is free first, and then we can do most of the things in R, including geospatial analysis. And if you have used R, this is not new. We need to we use many different R packages for different objective. And RStudio, that's a IDE, integrated development environment for R. So basically, using RStudio, we can change this to this. So it looks nice, and a lot of it looks good. So we use RStudio. And R Markdown, I think Dr. Matt Russell, I think he talked about R Markdown as well. So it's a file format that we can use to make dynamic documents with R. We can use install.packages to install R Markdown, and you can find other detail in here. And some packages that I commonly use in developing biomass models. Tidyverse, ggplot is within Tidyverse, but today the packages in blue, we'll use them in today's example as well. So ggplot, grid extra, recep2, beta reg, that's for beta regression, Dirichlet reg, that's for the Dirichlet regression, and system feed is for the SUR. All right, any questions? Looks like we got. All right, let's move forward. So assuming everyone has the data and our code as well, I think it will go quick because our code is already there, and then I have because I put the RMD file, so instruction is also in there. Let's start with the part 1, AGB models. Okay. And so in this example, we'll use linear regression model to predict above-ground biomass using DBH and total tree height. The dataset consists of information on component biomass. Foliage is denoted using FOL, branch using BCH, stem bark using BRK, and stem wood using STM. And the total above-ground biomass is labeled TAB. Of 32 Douglas fir trees, along with their diameter breast height DBH, live crown length LCL, and total tree height THT. This data set, I obtained that from this paper by Ney and Borman, 2014, and I think this should be available to everyone. It should be accessible to everyone as well. And the link is in there, so go to that link and try download if you want. So assuming most of you or all of you have our experience reading the data in CSV file, it's not a difficult task, but because this is an RMD file, and in this case I have saved the data and this RMD file in same directory, so that's why I don't need to specify working directory. Otherwise I would use set working directory SCT-WD for set working directory, and then provide path name or location of that file. This is where I have saved this data, and I will be reading this data as DF read.csv for reading CSV file. And in RMG, we can run this code in here as well. So that's how I read this. And we'll focus on above ground biomass in this example. total above ground biomass. First thing we'd like to do is with, for any data analysis, I start with basic plots and summary statistics, and also print some few observation. In R, we can use head function, HEAD head, and data frame name. So this will tell us, or this will print first 6 observation. And this summary function will print the summary of the data, okay, for all variables. So here, so this is the first 6 rows. We have ID, which is arbitrary ID for tree, DBH, diameter at breast height in centimeter. THD is total tree height in meter. LCL is the length of live crown in meter as well. Foliage biomass, branch biomass, bark biomass, and stemwood biomass. And TAB is total above ground biomass. And the summary is printed here as well, summary of the data. And we can see this summary of ID does not make any sense because that's for just arbitrary tree ID. Summary for the DBS, minimum diameter was 23.1 centimeter and maximum was 80.3, and so on. And we have similar summary statistics for other variables as well. So the next is we'll create some basic plots. We could use this base plot function in base R, but I'll be using ggplot here because it makes nicer graph than just the base plot. And I have loaded this ggplot2 package using library function. And if you have not installed ggplot2 on your computer, then you'll have to install that. Hopefully everyone has installed that already. If not, then you can copy this code and then put it here in front of that and then run that. Okay, but in my case, I have already installed it, so I don't need to run that code. Okay, and then to make it available, I need to do library ggplot2. And because we are interested in developing a model that predicts total above ground biomass, TAB based on DBH and total tree height, our dependent variable is TAB, and independent variables are DBH and height, which means the DBH and height will go on right-hand side of the equation, and TAB will be on left-hand side of the equation. And when we are creating a scatter plot, we will put TAB on y-axis and DBH and height on x-axis. And because we'll have 2 plots, that's why I saved first plot as P1 for plot 1, and second plot is P2 for second plot. And ggplot, that's the function, plotting function, and I need to provide the dataset name, which is DEF in this case. Aesthetic, I have x-axis variable, which is DBH in this case, and y-axis variable is TAB, total above ground biomass. And then I want to plot points, which will give me a scatter plot of points. And I can also label using xlab for DBH, or x-axis label, and y-axis label using ylab. And I like to use this black and white theme. If I don't do that, then it will print some kind of grays background, but I like this theme. That's why you can change this theme. There are other themes as well. And once I create this plot, I will print that plot and do the same thing for a second plot. And in second plot, I have, instead of DBH on x-axis, I have height on x-axis. So let's run this code and then see if it prints anything. So this is because we have 2 plots. One is DBH and total above ground biomass, and the second plot is total tree height and total above ground biomass. The relation between DBH and height looks more linear than total tree height and total above ground biomass, because we see that curved shape here. But however, we'll just move forward with the linear regression. And by running this, as we saw, we had, hold on. we saw that if I run this code, then we had two figures separate, one for dBH and the other for height. But it would be nice if we can put them in one. So we can use this grid extra package and grid.arrange function. And because I saved P1 and P2 as two plots, if I use this, then by default, it will make one row for one plot. So that's why we have two rows here. But in the second line, here line 58, I have grid.arrange, and I specify n row equals 1. So that means I want both plots in one single row, which means these will be presented side by side. So dBH and total above ground biomass, total height, and total above ground biomass. So that's just one simple plotting example. The reason for creating a scatter plot, why we want to create a scatter plot before we move on to model fitting. First, we need to determine, or we can tell if the linear model will be good. If even for total tree height and total above ground biomass, the relationship is kind of linear, mostly linear. But if we had seen very curvilinear relation, then linear model would not work. But in this case, I think the linear model will be fine. So we'll just move forward with that. And also by creating this scatter plot, we could see if there was one outlying observation. For example, if there was one tree with, let's say 300 centimeter DVS, then that would pop up, or that would be obvious to see in that scatter plot. So before starting any analysis, I start with the basic plots. And we don't see any problem. So we will move forward with a multiple linear regression that will predict total above ground biomass as a function of dBH in centimeter and height in meter. We can use LM function to fit linear regression. And here I will name this model as mod 1, first model, and LM is for linear model. TAV is our dependent variable. Dependent variable follows independent variables. In our case, independent variables are dBH and total height. And the data we are using is DF. Okay, so let's run this. And then we can view the result by using summary function. Looks like most of you guys have experience working with this LM function. But anyway, so we can use summary function and it prints the result. Okay, so we see that so this is the intercept, that's the slope per dBS, that's the slope for total height. And we see that height is not significant in this case. And the model R square is, adjusted R square is 0.95, so pretty good model, but height is not significant. We get the coefficient, but we also want to look at the residual plots. We'll look into that later, but here, other than the R square, this is the residual standard error, that's the root mean square error, or square root of the mean square error, which is sum of squared error divided by the degrees of freedom for error. And fitted values. So fitted values is if we apply the coefficient that we obtained here to our data set, what will be the predicted values? Predicted values for the model fitting data are called fitted values. So then we can use fitted function in R to get the predicted value for the fitted values for the data set. And I will save that predicted value as total above ground biomass underscore pred to indicate predicted value. And then within that head function, I will also include n equals 5, because by default, this head function will print 6 observation. Instead, I want to print just 5. So let's see if it will work. And it worked. So here, what we have is we have the same data set, but in this case, we have additional one column, which is for predicted total above ground biomass. One thing pops out here is total predicted total above ground biomass for this tree number 5 is -62. Of course, if a tree is if a tree has some deviates in height, we should not get negative biomass. So maybe there is some problem with this model, right? We will get into that, but now let's look at the residual. Residual are just the differences between observed and predicted values. We can plot residual using resid function or resid function or residuals function in R. ggplot on aesthetic on x-axis, I want the fitted values, and on y-axis, I want the residuals from this model, and I want the scatter plot, and I want the label and also title. And by using this h just equals to 0.05, it will center my plot title. So let's plot this. And so what we see is, one thing we saw is this model is predicting negative biomass, which is not good. And the other we see is the residual plot. Ideally, what we want is these points to scatter around 0 and not show any pattern. But here what we see is the residuals start to decrease, and then as they get close to maybe 1800 or something, then they start increase. So that means there is a pattern, so which is not good. And this is one of the common problem in biomass data, and it can be resolved using log function or log transformation of the data. So that's what we will do in the next lines of code. So basically, I'm creating another variable called ln_dbh by using log transformation of dbh, ln_tsd, which is log transformation of tsd, and so on. And then now I'll plot these log scale data for log dbh and total above ground biomass, and log total height and log total above ground biomass. And then I will create one row or one plot for that data set. So, and even without the log transformation, the relation between dbh and height and dbh and total above ground biomass and total height and total above ground biomass was linear, and with the log transformation, it is even more perfect. So now we can feed the model with the transform data. So basically, same as what we did before. But in this case, instead of using TAB, we'll be using ln_TAB as our dependent variable, and on log of height and diameter is the independent variables. And we are still using DF as the data frame. And summary of the model 2 will summary function will give us the summary. So let's run that. And now in log scale, height is also significant. R-square is even higher than that. We can extract adjusted R-square using this function summary, and then by adding this $sign adjusted.rdj for adjusted.r.square for adjusted R-square, and I'm using mod 1 here, so that is for on transform model, and for mod 2, which is for log transform model. So let's look at the R-square. R-square for adjusted R-square for untransformed model is 95%, and for the log transformed model, 99%. So in terms of adjusted R-square, that's good, but let's look at the residual as well. So I will do the same thing as we did before. ggplot, fitted values on x-axis and residual on y-axis, point for dots, and then black and white theme, and title. And then if I look at this residual plot from second model, we see it has better residual properties than the model 1. It will be helpful if we plot those two plots side by side or up and down. So now we can see that. So now we can compare. This is for model 1 and that's for model 2. Obviously, the model 2 has better residual properties. So basically, log transformation is helping us. And some notes on log transformation. Of course, we saw that R-square was higher, and also the residuals are better than original scale. But when we do log transformation, then our predicted values are in log scale. And when we transform back into original scale, then there will be some log transformation bias, and there are several bias correction factors people have suggested. And one common is calculating this EXP MSE over 2, and then multiplying the predicted value by this value. And we'll not go into too much detail on that, but if you, for example, even if you read my paper as well, you'll see how we applied that. So, and another advantage of using log is because when we get the predicted value, we have to back transform using exp function. And when you exponentiate anything, then it will become positive. So we will not get any negative predicted values from log scale, log model. And that's all for the, if we had a deviation height, and then we wanted to predict above ground biomass, total above ground biomass using linear model. Probably, I think, given the time, should probably just move on to the next, which is component biomass, I believe. Okay, second is component model. All right, so let me share this screen again. Okay. And then, so in this case, what we'll do is we'll do the same data set as in part 1. And yeah, I think it's kind of too fast for some, but our code is already written, so you can look into that in the future. Is that fine, Joshua?
Perfect.
Yeah, because we've been already here for close to 3 hours. So yeah, 2 hours or so. Yeah, and so the second is the component biomass models, right? So in this case, we'll be using the same data set. Let's read that data, and then because now we are interested in component biomass, so let's plot the components, okay, instead of total above ground biomass. Once again, I'll be using ggplot2 and grid extra. Okay, of course, there are other options, right? R is open source. And one of the advantages of that is there are many options, and the disadvantage is there are many options. Okay, so if there is only one option, then everyone will be using the same option, so it will be universal. But there are multiple options, so the method I use may not, you may not like that method, and so, but there are multiple options. And here STM for the steam wood biomass, and data is DF, and DBH on x-axis. On y-axis, I have STM, steam wood biomass. Do the same thing for bark, branch, and foliage, and then use this grid arrange function and put all those plots in one. Let's run this code and see if it works. Okay. So here we have DBH versus steam wood biomass, DBH versus stem bark, DBH versus branch wood, and DBH versus foliage. And then second, I'll plot I'll create similar plot, but instead of DBH on x-axis, I'll have height, total tree height. Okay, and then I can run that code. And as we saw before, for the total above ground biomass, we saw slightly curved relation, then slightly curved relation of deviation and height. Height and total above ground biomass. We see similar kind of pattern in component biomass as well. And we found that if we use log model, then it would be better. So that's why we'll do log transformation here. And then, so for the log DBH, ln log function and DBH, that's my independent variable. And I do that for all the dependent and independent variable. Okay. And now we will fit a system of equations. So in this case, we'll be fitting SUR. And as we discussed during the presentation, nonlinear system fit does not work that well in R. So that's why I use SAS for that. And even for linear system of regression, I would use SAS, but SAS is not open source. It's not freely available. It's expensive. So for this example, we'll use system fit. And so here, what we need to do is first that SUR is available under system fit library or package. So we load that library, and then I create my system, which will be a list of all these component models. STM will be a model that will predict natural log of stem wood biomass as a function of natural log of DBH and natural log of total height, and do the same thing for other. And you'll notice also I changed for the foliage here. Instead of using total height, I use live crown length as independent variable instead of total height. Okay. And then once I type these equation, then I create a system using list. And then my stem model is STM, stem bark model is BRK, and so on. So let's run that. And this is just, these are just the information. So this is not an error. Please cite, if you use this package, then cite that is that and all that information. Okay. And we can, within the system fit, we can use OLS, which is same as fitting 4 different equations, or we can use SUR, which simultaneously fits equation. OLS, if you specify OLS here, then it will fit those equations kind of independently. And if we specify SUR, then it will fit as a system. So let's run this code. System fit, that's the function. And then system, we created that system here. And then this is the method that we will be using, OLS, ordinary least square for this case. And the data we'll be using is DF, okay? And then summary, same as in linear model. And now we have this OLS-based estimate. And this is, like I said, same as what we would get if we were fitting one model at a time. We can verify that by fitting a model that predicts the natural log of foliage based on DBS and height, DBS and crown length. If you run this code, this is LM function, and the coefficient here and the coefficient here, they are same. Foliage model is same because we specified OLS function. But we want to fit them as a system, and we want to specify SUR. So we just specify SUR here. And in addition to what we already had, here we'll get this variance covariance matrix of the residual. And our assumption is the correlation between the residuals among those equations is high. And we can see that too. For example, stem bark and stem wood residuals, their correlation is almost 99%. So, and so on, we get all these parameter estimate, which is same as if we were fitting simple linear multiple linear regression, but we have for multiple models. So this is equation 2. Equation 1 is stem wood model. Equation 2 is stem bark model. And equation 3 is branch model, and equation 4 is foliage model, and so on. Okay, yeah. So that is all for the system of equations. Let's see, I have some questions here. Let's see. Okay, yeah. Okay. All right. Good. As I said before, given the time, plus we already have the data and our code in that drive, so we can just move forward with the other approach. So the third option is to use beta regression, okay? And for that, I know we are moving fast, but okay. So in this case, what we will be doing is, instead of predicting actual biomass, okay, yeah. Instead of actual or in kilograms, we'll be using percentage, okay? And let's read the data. And for this, I actually don't need this reshape function. I don't need to modify the way I have modified data here, but this is another way of modifying your data, right? So basically, I'm reading data, loading these R packages here. Let's do that. And then here, what I'm doing is, right now it is in, the data set is in wide format. And now I would like to change that into long format, which means instead of having data this way, I'll have this way. And then calculate percentage as well. Calculate percent is by dividing mass by the total above ground biomass, okay? And then, so as you see here, so earlier we had 32 observation, but now we have 32 times 4, which is 128 observation, because we have 4 components, okay? And now we have component foliage for all the trees, and then mass is, this is the actual mass, but this is the percentage. So for example, for tree number 4, there is only 2.9% foliage biomass, and so on. And then the next is just simply using beta reg function, same as what we did in LM function, okay? So because now it is one data set with all those components, I have to subset and just use the foliage if I want to feed the foliage model. So subset data frame and just select the foliage component, comp equals foliage. Okay, that way I'll have just 32 observation in this data set. And then I can also feed the linear model using the percent as the dependent variable and DBH and LCL as the predictor variables. And optimal, or the better, is to use beta regression. And these are the parameter estimates. This is for the linear model. And these are for the beta regression. Okay. And there is a lot of information. Of course, you can look at the documentation for beta regression by, for example, if you type beta reg, and then question mark beta reg, then you can see all that information in help document. So do that as well. But now let's compare the fitted lines of the beta regression and the linear regression. Yeah, this is warning message, but it's not a problem here. Just suggesting to use line width instead of size. Okay, so here what we see is the linear model is in green and the beta model is in red. Those are the two different lines, and beta regression has a slightly curved shape than the linear model. And we can do the same thing for bark. Bark, we subset that using the subset function and fit linear model and fit beta regression model. Can do that same thing. And now let's compare the fitted lines. They are almost identical except for upper and lower limit. Okay, and here we may not have that issue, but one challenge if we fit linear model for the percent data is sometimes the predicted proportion can be greater than 1, which is illogical. So we don't want to use that. If it is actual biomass, then linear model is fine. But if it is percentage, then of course we can use some transformation, but beta regression is better. And this is for branch biomass, branch wood. And once again, we have coefficient from linear model and beta regression model. And then we can use this plot function to plot that. Plot the fitted and fitted lines. Okay. And I forgot to mention here, because we have two independent variables. So what I did is I fixed one independent variable to its mean. So this graph is basically telling us how will the branch biomass change for a given mean, deviates, and different live ground length. Okay. So increasing live ground length should increase branch biomass, which is what we see here. And for this stem wood, we do the same thing. And then let's plot the, here again, we fixed deviates to its mean value. And then we change we let the live ground length vary. And we see, and this makes sense too, because if we have increasing live ground length, so that means the proportion of stemmed biomass will be slightly smaller, because now we have more biomass in ground. Okay. And by default, beta reg uses logit link function, but we can change that into other link function. And for example, if I wanted to use log link function, then I just specify link equals log inside this R code. Okay, and then I can get the same similar coefficients. And the only difference is when we get the predicted value, then instead of using logit, back transformation of logit, we would transform using exp in the log model. And let's see. Okay. And then now let's look at the final approach, which is the using Dirichlet regression model. And let's see. So in this case, in first example, what we did is we used the total above ground biomass and fitted that independently. And in second, we used SUR and fitted component biomass simultaneously. And in third, we fitted proportion, but independently. And in fourth, we'll be fitting proportion equation, but simultaneously, okay, together. Okay, so once again, same data, same packages so far, and calculate proportion by dividing component biomass by total above ground biomass here. Then let's plot all components in one figure, basically using DF data, and then plotting points and lines of component, foliage component, branch component, stem bark, stem wood, and then labeling that. Okay, so if we do that, it's taking some time, but now we have all the figures or all the component in one. So with increasing deviates, there is not that great trend, but we see that this is stem wood biomass that's slightly declining, but not a lot. But take note that this is percentage or proportion. So 80%, from 80% to more than 80% to 70%, and so on. And the red one is branch biomass. So increasing DBS is kind of increasing the branch biomass. Interesting. And then we can do same thing for live ground length, which should give us more obvious trend than that, and which does actually. So increasing live ground length, our proportion of stem wood biomass is decreasing, which is same as increasing branch biomass. That's what we expect. And now to feed the Dirichlet regression, first we need to format the data so that the Dirichlet regression or Dirichlet function can read that. So we can use this dr_data. And in this case, we have 4 different components of 4 different dependent variables, and we want to feed them simultaneously or together. And we have y values or 4 component biomass in column number 5 through 8. If I look at here, column number 5 is foliage biomass, 6 is branch, 7 is bark, and 8 is stem wood biomass. So that's why I need to specify that our y values are in DF data frame and in column 5 through 8. And by using this, I'm telling R that I want to format this data set to be ready for data analysis using Dirichlet regression. And then once I do that, then I can use this Dirichlet function, and then same approach is in linear model, dependent variable as a function of independent variables. Okay, and then there is some warning messages, but cannot create a class to data frame. So let's see. For some reason, this is giving me some error, but it should work. Let's see. Yeah, it worked. So yeah, that's a warning message, but looks like we're fine. It's giving us the result. So now it basically fitted for 3 different models, and one model is not. If we know the proportion of other 3, then we can get the 4th proportion. For example, if the sum of 3 proportion is 75%, then the 4th will be 25%, and we can use similar approach in calculating that. And so by default, so in our data set, if we look at this, this is can't view, let's see. So by default, what R does is uses the first appearing component as the base or reference group, but we can change that using base option here inside that Dirichlet function. And here I'm using base equals 4. That means the 4th component, which is in the data set, it will be stem wood, and that will be our reference group. That way we can get coefficient for all other components. First, I need to run this. Let's run that. For some reason, this is giving that error message or warning message, but if I run, if I close everything and then rerun it, it will work. So that's not an issue. So once we get that, then everything getting predicted value is the same as in linear regression model. We use fitted values, and then that's the slightly different is because we have 4 components, so we have to specify what component do we want. So basically here what I'm telling is I want to create P-fold predicted foliage using the fitted value from Dirichlet regression, which I named Diri1. And because it is foliage, so select the foliage component. Okay, and then do the same thing for bark, branch, and stem wood. And then now we can create a plot.
Sorry.
So now so this is a lot of course, but the objective is plotting observed on x-axis. Yeah.
Just a quick question. For the results for the Dirichlet, a little bit up, it doesn't matter whether the variables are significant or not.
I'm sorry. Oh, does it matter if the variables are significant or not?
For the results of Dirichlet, if you go up a little bit, we have the results for the branches, for the stem, or yeah, for the bark. Yeah, okay. It's this one. If you watch, you can see some are not significant. It's not important. What else?
Yeah, that's a very good question. And here I didn't. So I just use one set of predictor variables for all components. But if you look at the documentation for Dirichlet regression, you can specify. For example, you can just specify DBH as the predictor for bark. You can do that if you wanted to. And in regression, sometimes, I'm not too worried about the significance of the predictor variables because those are the commonly used predictor variables, right? So deviation height or deviation live ground length. So I still use them even if they are not significant.
Okay.
Yeah.
Okay.
Yeah.
Thank you very much.
Yeah. And so basically here I'm plotting those period values, observed value on x-axis and predicted values on y-axis and giving title. And so those are the one-to-one line. And we can do that same thing by setting live ground length to its mean and changing DBH. So this is, once again, this is many lines of code, but the objective is to create new data for which the live ground length will be same as what is the mean live ground length in our data set. And for the DBH, we will use different DBH. And that's so basically for a given DBH, given LCL, changing DBH, we see that trend. So increasing DBH, stimulus proportion is increasing. And we do that. Now, instead of fixing LCL, now we are fixing DBH and then changing LCL, live ground length, and then plot that. And now we see this declining trend on stimulus and increasing in other. And the other thing to note is these are components. So if one increases, then the other has to decrease, right? Because there is only 100%. If one is 99%, and if it increases to 100%, then the other will be 0. So that's they will be negatively correlated. Then for the regression or the diagnostic plots, we can plot fitted values and residuals on for the foliage model, because foliage is first component, so that's why 1, and residue and branch is second component, so 2, and so on. And then we create this plot. So it looks like the model is doing fine, and we could use this to predict proportion. So I think I know that was too fast, but I hope that was informative. And if anyone has any question.
Okay. Before we go into the question, Professor, thank you very much for
no problem.
the wonderful presentation you have made. And I can see that you have talked for such a long hour. So because you love to take some questions, but I will just restrict the questions to just 1 or 2 questions, or just let's make it 2 questions so you can just answer this question and go take a rest.
Sounds good. Thank you. I think I talked too much. Yeah,
you talked a lot, exactly. So for me, in most of my classes too, I have been advised not to talk more than 1.5 hours. So anything beyond this, then I'm off. So
yeah, we took 5-minute break, but this is not everyday thing. So
yes.
Yeah. If anyone has question, we can take 2. Yeah. Otherwise, we can. I mean, I provided my email address, so if anyone has a specific question, then they could reach out to me as well. So
exactly.
Yeah.
So in the absence of no question, let me on behalf of the organization say a big thank you to you, Professor. And I also want to acknowledge the presence of some of my friends and senior colleagues that are here. I know there is someone who was asking a question. I know he's asking a kind of question that is advanced, and some young people in this place, some young students may be wondering, how come about this? What does it mean? But it's something, again, that we can all go back to the video and rewatch. And like we promised to also share this video on our social media platform, especially on our YouTube page.